Ladies and gentlemen, good evening. My name is Xue Suijian, and I'm Deputy Director of the National Astronomical Observatories of Chinese Academy of Sciences, a sponsor institute of this New World, New Horizon Astrophysical Public Series. Thank you all for your coming and joining us here tonight. I'm so delighted to introduce our distinguished guest speaker, Dr. Gary Sanders, who is not only a world-renowned experimental physicist, fellow of American Physical Society with more than 200 publications, but also one of the most accomplished project managers of the scientific mega projects. Dr. Sanders did his undergraduate study at Columbia University. In 1971, he received his PhD under the supervision of 17, Ding Zhaozhong, in physics from MIT. It's a US version of Tsinghua, I think everybody knows here. He becomes assistant professor at Princeton University later on. He started his career in experimental physics, working on particle physics with 17 in Germany, and continued their collaboration on SSC, or the Superconducting Super Collider, as the project manager when he moved from Princeton University to Los Alamos National Lab. SSC was actually a pioneer project of the most famous Large Hadron Collider, or LHC, operating at CERN, the European Organization for Nuclear Research in Geneva. He joined LIGO project in 1994, before the project was fully funded by the National Science Foundation, and governed the project as the project manager and the deputy director for 10 years. During this period, the LIGO project enjoyed substantial progress and conducted multinational collaborations. In 2004, he was appointed by Caltech as the project manager of the 30-meter telescope. Since then, he has successfully led the design and technical development and get the project ready for construction. As we all know, this year, the LIGO project announced the first detection of gravitational waves. Because of his significant contribution to the early stage development of the LIGO project, Dr. Sanders shared the 2016 Special Breakthrough Prize in Fundamental Physics as a former project leader with the rest of the LIGO team. Congratulations to Gary Sanders. Undoubtedly, we expect his next great success in leading TMT, the 30-meter telescope, to become a powerful tool of exciting discoveries. I believe Dr. Sanders may be the only person in the world who can share stories about the mega science projects from SSC to LIGO to TMT. So please join me and give a warm welcome to Dr. Gary Sanders.
Thank you, Suijian, for a very nice welcome. I'm really honored to be here. I'm delighted to be here. I'm a past collaborator with scientists from Tsinghua University. I met one of my old colleagues from Tsinghua from the Super Collider this evening, and I'm very glad to be here again tonight. Listening to the introduction, it seems like I've been around for a long time, and I've had a long career, but I'm still having fun. And one of the things, I have a few messages for tonight. One of the things I've come to learn in science is to try to work in science that will look at the universe, the physical world, the universe, in a different way. And when we see the universe in a different way, we will usually see a different universe. I have said this so many times that I find that people are quoting me in books. This book by Michio Kaku quoted me, "Every time we have looked at the sky in a new way, we have seen a new universe." And I've been lucky to work on a few things like that, like LIGO. And I'll give you a few examples. So that's the first lesson I want to talk about tonight. We think back to astronomy. Throughout human history, up until 1609, all astronomy was done with the naked eye. And we know that the aperture of the naked eye is very small. It cannot collect very much light, cannot see very far. But in 1609, Galileo used the telescope idea from Lippershey, and he used a lens about this size. It was a big advance, and what he saw was a different universe. Everything wasn't going around the Earth. The planets were going around the sun. It was a different universe, and it caused a great deal of controversy and arguments for which he paid a price. He also saw many interesting things in astronomy, and he started astronomy with refracting telescopes. But he looked at the universe in a different way, and he found a different universe. Another example is in about 1931, if you were in New York City and you wanted to make a telephone call to London, the telephone company would send your call by radio. And it was very noisy, a lot of static. So the telephone company asked this scientist, engineer, find out where all the static is, and perhaps we can make the calls cleaner. And he built this antenna with wheels from a Model T Ford, and he mapped the radio signals from the sky, and he found the radio from the sun, and he found radio waves from storms, electrical storms, but he found a source that didn't repeat with the rotation of the Earth, the 24-hour day. It was the sidereal day, the day that astronomers know. And he published a paper observing the brightest it was very bright also, very bright radio signal. Observed the brightest radio signal on a sidereal day, and he published this paper, Electrical Disturbances Apparently of Extraterrestrial Origin. He had seen a different universe. And interestingly, the optical astronomers in those days said it has to be wrong. Okay? They weren't ready to see a different universe, but he saw one. And we now know that it's Cygnus A, and what he was looking at was a system powered by a black hole and jets of gas and shock waves, radio sources, a different universe, something that hadn't been seen before. So that's another example, looking at the universe in a different way, seeing a different universe. Now, it was mentioned that I worked in high-energy physics on the superconducting super collider, and Tsinghua University was part of the team that I was part of. This is a picture of a detector that was to be built 32 meters long, 19 meters in diameter, a very big detector which wasn't built in the end because the United States didn't finish the project. But most of our colleagues went on to CERN, to the ATLAS and CMS detectors at CERN. And what we were going to look for, among many other things, was the Higgs particle, the particle responsible for mass in the Standard Model, and many other things. But this also was looking at the universe in a different way. And of course, many years later, after running the Hadron Collider, in one of the first runs, the Higgs particle was observed. This is a very clean event where you have the quark annihilations producing a very clean signature of 4 muons, a beautiful event. And the Hadron Collider is coming on now with a higher energy and luminosity. And we will see that they will see not the Higgs that we were looking for, but we will see things that aren't expected, and I'm sure of it. They will see a different universe, even though finding the Higgs is a remarkable thing. But another point I want to make about that effort, unlike Galileo, unlike Karl Jansky, to do that kind of science took a very big collaboration. So the Atlas team, one of the two teams, has about 4,000 authors on the paper. And so the second theme in my talk is to do the work of seeing a new universe very often takes a very big investment in money and in intellectual power, very large collaborations, international collaborations, more and more. And the Large Hadron Collider is an example. So let's talk for a few minutes about what it takes to go from one scientist to many. So this is a picture of an astronomer painted by the Dutch master Vermeer. He's alone in his room. He's thinking about the universe, and that's the example of small science. He may make a very big discovery, but it's a small group, perhaps just him or him and a few assistants, some students. And let's look at another scientist also painted by Vermeer. If you study Vermeer, you'll see he does many paintings in this same room. This is a geographer. And imagine that these two scientists want to work together on some problem in perhaps astrogeology, how you form planets and do the astronomy to understand this. So they would have to work together, okay? Now Vermeer didn't paint this. This was done on the computer at Caltech. But putting them together in the picture is pretty easy. But imagine what it takes to have them work together and produce science together when they come from different fields. It's already a very difficult problem. So the first guy, the astronomer, he works alone as a researcher. He has not only the knowledge that you can learn in astronomy from books and papers, but he has what we call the tacit knowledge, the knowledge that comes from working in the field and talking to people and learning what people do and who's good and who's not so good and who gives correct results, the unwritten parts of the field. This is part of the expertise of being an astronomer or any individual scientist. He knows about the community and the shared history of the field. He's an expert, but in a narrowly defined field, in this case, astronomy. But with all this together, he can contribute to astronomy. He can write papers with new results. Now, if you put the two of them together, you have two different scientists with different histories. They have to learn to talk to each other. They have to interact. They have to learn just enough about each other's fields so they can talk to each other and make judgments together. And if that works, they can contribute to the joint science, the interdisciplinary science. That's already hard to do, although it's not that uncommon. Think about that Large Hadron Collider project with 4,000 scientists and engineers and business people, lawyers. I see one lawyer right here in the front row. Hi. And a project manager. What is a project manager? Might be a scientist, it might be an engineer, but it's someone who's an expert at making it all work together, but is not necessarily the most expert scientist or engineer in the group. Okay, so it becomes a very complex problem of sharing and respecting different expertise. It's essential, though, to modern large science. So when we train scientists, we train them to achieve science. We don't necessarily train them to work in groups or to make decisions or to respect people who make decisions. So an individual scientist is trained to live up there, to achieve the best science, to publish the best science. But if you're going to do a CERN experiment to look for the Higgs particle with 4,000 scientists, you have to have a team that can do all of these. Work together and share the work. Okay? Good. Work together and share the work, affiliation, and also respect decisions. Even when you disagree with the decisions, make the decisions of the leadership successful. That's a skill. And they don't teach you that in graduate school. So with that introduction about what it takes to put a large team together, let me give you two examples from my own career, projects that I've worked on as the project manager, and it was mentioned that I was the project manager for LIGO, and I'll talk a little bit about that, and then I'll talk about the 30-meter telescope. And of course, LIGO begins with the idea that Einstein gave us in 1915, that gravitation amounts to a curvature in space-time. And so that when this small object falls to this large object, it's equivalent to falling down into the curvature of space-time. A year later, after publishing general relativity, Einstein published a paper in which he noted that if there's massive objects engaged in a violent interaction that disturbed space-time around them, that disturbance would propagate away from the source of the interaction at the speed of light. This is gravitational radiation, and he wrote in his paper that if we saw this on Earth, it would be very small. It's unlikely to be something that we would detect. And he told us what kind of radiation it would be. It's not dipole radiation like you would see in electromagnetic radiation, but the lowest order is quadrupole radiation. I'll talk about that in a second. But around the time of the 1970s, people began to think very seriously about how to detect this disturbance. Here's two neutron stars orbiting each other and spiraling in and disturbing the space-time around them, and the radiation is carrying away energy from the system. That's why they're spiraling in. And that radiation is traveling out at the speed of light, and it should be possible, if you have a sensitive enough detector, to detect it on Earth or in space near Earth. And you can do it either way, and you're sensitive to different frequencies of gravitational waves. And so LIGO is an interferometer on Earth. It's basically a device for measuring the separation of these two mirrors and these two mirrors. And we learned from gravitational radiation from Einstein's 1916 paper, in fact, that if the gravitational waves pass through this and they look like this as quadrupole radiation, this pen would get longer. At the same time, the other dimension would get shorter, and then as the wave proceeds through, this would get longer, and this dimension would get shorter. So it's an oscillating behavior, and what it means is one arm would get shorter in one part of the wave, the other arm would get longer, and if you can measure the separation of these mirrors using an optical interferometer with sufficient precision, you ought to be able to detect the gravitational radiation. Very challenging problem, which I'll tell you about. So in LIGO, we set out to build two of these interferometers because no one would believe a signal seen in one. And they're 3,000 kilometers apart in two different places in the United States. And they look like this from an aerial view. The mirrors that you're measuring the separation of are 4 kilometers apart. So the total length of the two systems is 16 kilometers. This is the one in the state of Washington. And the sensitivity to the distortion of space-time in advanced LIGO, the system that's on now in the same facility, is a part in 10 to the 23rd. That's extremely sensitive. It's very challenging to get there. And in length, with 4 kilometers, it means a sensitivity to a change in the arm length to 10 to the minus 19 meters. Now, not everyone here is a scientist, so I'll just point out that compared to a meter, a human hair is about 10,000 times thinner than a meter. And the wavelength of light, 1 micron light, which is the light in LIGO, is 100 times smaller than that. An atomic diameter is 10,000 times smaller than that. A nuclear diameter is another 100,000 times smaller than that. And the sensitivity of advanced LIGO is 10,000 times more sensitive than even that. So that's a rather remarkable sensitivity, and of course it has to be achieved given all the disturbances around it, shot noise, vibrations, seismic noise, the internal KT noise in the mirrors and so on, but that's the technical challenge of LIGO. And to build this project, we had to manage the construction of the world's largest ultra-high vacuum system, 16 kilometers of arms, all these vacuum chambers to hold the mirrors in the interferometer. We had to build mirrors that were polished to a precision 6,000 times smaller than the wavelength of infrared light that was being used in LIGO, 0.16 nanometers RMS. Here's some pictures of some of the mirrors being installed in the initial LIGO. There's even a picture I found with me doing one of the installations in one of the minor mirrors. No one lets me do that anymore. And when this system turned on, the goal was to try to detect spiraling neutron star systems or black holes, which would spiral in and lose energy to gravitational waves and make a kind of chirp signal. These are all at audio frequencies. Whoop, a signal like that. Or something like a spinning neutron star that has an eccentricity or a bump on it that would make a sine wave signal. Or a collapsing object like certain kinds of asymmetric supernova collapses. It has to be asymmetric because we're talking about quadrupoles, for those who are thinking about that. That would be a burst, a crash. Or the staticky gravitational wave background from the Big Bang. So we built this system to detect any one of those things, and as many of you know, what was seen was actually quite striking. Two 30 solar mass black holes spiraling in. It all happened in about a third of a second. These are 30 solar mass black holes that were moving at half the speed of light. And they merged, and when they merged into a single black hole, 3.5 solar masses were missing. That's what had been radiated into gravitational waves. So that was a signal seen in September in an early run of advanced LIGO. And the signals detected at the two interferometers looked like this and like that in the two observatories. And when you do the calculations with numerical relativity, you get signals like this, so they look very much the same. Really quite remarkable. And so a paper was published in February, and that's the paper that Sui-John just mentioned, and most people know about it. The really striking thing is, aside from the statement that this is the first direct detection of gravitational waves, it's also the first observation of binary black holes mergers. I even like to say it's the first direct observation of black holes, radiation directly from the black hole, okay? But it's in a binary system. And as I said, 3.5 solar masses were radiated away. And it does say in the papers that for a very brief portion of a second, the energy that was radiated away was brighter. It exceeded all the light from all of the stars in the universe. So we're talking about seeing a new universe. Even though we were looking for black holes in spiraling when we set out to build LIGO and to run it, these were more massive and farther away, 410 megaparsecs, between 1 and 1.5 billion light years away. A real surprise to the team. And we're talking about a very violent and dark universe. The system that's being seen is a very different universe. This wasn't expected. And the other point I want to make about this is there were 1,005 authors on that detection paper. So this is big science. When I started with Barry Barish in 1994 at the early part of the LIGO project, the total number of people working in the area were about 100, okay, worldwide, maybe 150 or 125, but of order. Now it's a big community. The masthead for the team is very broad in the world. And of course, we're going to see now, especially because there's been a detection, a network, not just the two LIGO detectors, but the advanced Virgo detector will be on later this year. Presumably, the Japanese are working on a cryogenic version of this detector, which actually may have some more capabilities. And the third LIGO antenna has been provided to India, and they will be building a site to host it. So there's going to be a network which, if they're all running, will be sensitive and be able to point better in the sky at these sources. So this whole new field of astronomy is open. It's going to look at a different universe, and I know there's interest in China in becoming active in this. The ground-based terrestrial interferometers looking for gravitational waves in the audio frequencies, the space-based antennas looking in the much lower frequencies at much more massive binary black hole pairs, for example. and there are pulsar timing experiments. This is going to be a study of a new universe. That's what happens when you look at the universe in a different way. So let me talk about the 30-meter telescope, which I've been working on since 2004. It's a project that involves 4 countries, Canada, China, India, and Japan, and 2 universities, my own university, Caltech, and the University of California. And of course, the goal is to build a telescope with a bigger mirror than has been done before. You can collect more light, and with diffraction theory, you can get better resolution, sharper images. All you have to do is remove the disturbances of the Earth's atmosphere, which we can now do with adaptive optics from the ground. So we don't need to build the Hubble Space Telescope. We can do a better job, considerably better job, with a ground-based observatory and adaptive optics and a much bigger mirror. So to compare with Hubble, the 30-meter telescope, if you take the Hubble telescope and looking at the very deep field, far away in the universe, light that's been traveling for the longest time, when the universe was about 10% its current age, you can look at some of these galaxies, very old, young galaxies, images of the early universe. You can see with Hubble this kind of resolution, but from the ground with TMT you'll be able to see this kind of resolution. So right away you know this thing can see more and perhaps observe a new universe. The telescope looks like this, a 30-meter diameter mirror. Light comes in, it's focused up to a secondary mirror, to a tertiary mirror, and onto these platforms where there are cameras and spectrometers to take the data. It, too, is an international project, and just some of these flags tell you that many of the parts of the system are being designed and will be fabricated and delivered and integrated by partners. And I've shown you Canada, China, India, Japan, and those of us in the United States. So the dome, a remarkable design for a very important thing, the enclosure of Canada, the telescope structure by Mitsubishi in Japan. You can just see some beautiful images. And you can see early fabrication of some of the complex joints. The mirrors, the 30-meter diameter mirror is made of 492 separate mirrors, all mounted, sensed, and controlled to 15 or so nanometers so that it acts as one optical mirror. Glass is already in production for these segments in Japan. Mirrors have been polished in the United States. They're in production in Japan at Canon. Here in China, in Nanjing, they've already made a full-size mirror and several smaller mirrors, and they're putting together the system to manufacture mirrors here in China. And our colleagues in India are also producing a factory to do the production starting next year. Now, all of those mirrors will come to the United States where they'll finally be measured and adjusted and then mounted on the system that will support them and make sure that they're aligned perfectly under computer control. That system is designed by the Jet Propulsion Laboratory, and much of it will be built in India. So you can see the national flags on many of these systems. The tertiary mirror, the science steering mirror of the system that makes TMT an agile telescope. We can quickly go from one instrument to another as conditions change and be agile in our scientific program. Will be done here in China. It's already being prototyped in Changchun. And we have work on the adaptive optics system to sweep away the disturbances of the Earth's atmosphere. Some of that work is also being done here in China. The Laser Guide Star facility to bring the laser light that produces artificial stars, which we use as a standard in focusing the telescope against the Earth's atmosphere disturbances, being designed and will be produced in Chengdu. And the Guide Star lasers are under development at TIPC here in Beijing. And the instruments also involve a global community. And I'll just quickly flash some pictures of our infrared imaging spectrometer, an adaptive optics assisted instrument, an infrared multi-slit spectrometer also assisted by adaptive optics, and a large seeing limited spectrometer and imager that will also be among the 3 first light instruments. The system can hold up to 8 instruments. And the Chinese community is involved in that last instrument in particular, and just grabbed a picture from a meeting here at NAOC in Beijing 2 years ago, just about 2 years ago, in the early stages of the work on those instruments. So TMT is also a big global project. It has a lot of reach, and I'll talk about it in a second, that promises that it will also see a new universe. But how do you carry out these kinds of projects? And I'm not going to give a lecture in project management here, but the methods that I used on LIGO, that I used on the Super Collider project before, and on projects before that, we're using on TMT to try to make sure that this big international collaboration makes it right, puts it all together, and does it for the cost that's promised. And so you start these projects by taking all the pieces and breaking them down into a product tree so that you know every piece. And this just goes down 1, 2, 3 layers in this tree, but in fact you break it all the way down about 7 or 8 layers deep. This was from the Super Collider detector. So the first thing to do is organize everything that you have to deliver and work on in the project. This is from LIGO, a similar diagram. And from TMT. Every part of TMT fits into a diagram that shows you all the pieces that have to be delivered. And in fact, it goes lower. Every one of these things is divided further and further and further into a very detailed definition of all of the work and all of the products that have to be delivered to make the system work. How do you hand off something to China to be built and delivered to the US so that it'll fit? How do the Indians produce the supports for the mirrors and send them to China so the mirrors can be mounted? And how do you know it will fit? You analyze every dependency of every system on every other subsystem. So if you have n systems, there are potentially n square relationships. So this is called an n square diagram. It's actually n square over 2 because the other side is trivial. And you have to then write down a design and a specification so that every team working knows how to deliver things that will match the neighboring related subsystems. Highly organized. That's modern project management. How do you organize that work so that it happens? You make an agreement between the project and every institution on every one of these pieces of work, called a work package agreement, where you write down the design, the statement of the work, the schedule, the costs, who the key people are, when things have to be delivered, what they are. And you do this annually and you update it, and then you manage to that. So it's highly organized. It works. Imagine how far that is from Vermeer's astronomer. He never thought he would have to work in such an environment, but that's modern mega science. Okay? And it worked in LIGO. When we built LIGO, we had a plan that looked like this, and when we were finished, all of the deliverables came close to schedule for about the right cost, and obviously the system worked. So mega science can be done with modern methods of project management. And we did it in LIGO, they did it at the Large Hadron Collider, and we're doing it in TMT. Now as we go forward, what's the science of TMT? I've told you that with TMT we will see farther and sharper than Hubble. And I've told you that while we can see the earliest galaxies here, as in the Hubble Deep Field, that's going back to perhaps the universe being 1 billion or 2 billion years old. But TMT will be able to see further back. Okay, the universe, early universe was opaque. And at some point, the electrons and the protons, things were cooled down enough, the electrons and protons combined. And the universe became transparent, but very dark, about 300,000 or 400,000 years after the Big Bang, the Dark Ages. And at some point, things began to accumulate so that things heated up and began to reionize. And the first stars were born, cosmic dawn, a few 100 million years after the Big Bang, further back than those Hubble Deep Field images in time. TMT will be able to see back to cosmic dawn. TMT will be able to image Earth-sized exoplanets in the habitable zone, planets that have the right relationship to the star that they're traveling around. And here's some images of planets, exoplanets that have been imaged by Keck, and this has been done by Gemini and others, But we will be able to look for the light from the atmospheres of those planets and look for these kinds of molecules. And if you see these biomarkers, the kinds of things, oxygen, methane, water, oxides of nitrogen, if you see the right ones and the right combinations, you have a pretty good reason to believe that there's life on those worlds. So that's another exciting piece of science that TMT can do. But I actually think what we will see is not on that list. Well, we may see those. We will see things that are more surprising. That's what I've learned in my career of going from one high-energy physics accelerator to another more powerful one, and then on to LIGO and so on. Again, every time we've looked at the sky in a new way, we've seen a new universe, and I think TMT will be very exciting that way. So how are we going to do it? The last thing I want to say in this talk is to remind you that LIGO took a very large worldwide collaboration, and the Large Hadron Collider took a very large worldwide collaboration. Each team of the two teams was about 4,000, and I think TMT is already a global collaboration, and it will be a very large team that will see a new universe. And I grabbed this picture from this optics conference that's happening this week in Beijing, but that's the kind of collaboration that is needed to see a new universe, and I'm really glad to be here and to work with you all in China on TMT. Thank you.
I guess there were quite a couple of questions. Please.
Dr. Sanders, I just out of curiosity, where are you going to deploy the TMT? Is this a space telescope or is it ground-based?
Yeah. So the plan has been since 2009 to build TMT on Mauna Kea in Hawaii. And if you read the newspapers and watch television, you'll see that there are political and legal problems now in Hawaii.
Yeah, I've been there.
And so we are still working on the permissions to build in Hawaii, but at the same time we're studying other locations. And sometime within about a year, we will choose the place to build TMT. We're ready to build, but we have to sort out the location.
Okay, the second question is, if it's not a space telescope, how come its image is sharper, it's clearer than the space telescope, like a Hubble telescope or James Webb?
The Hubble telescope mirror is 2.5 meters in diameter. The James Webb is what, 6.5 or 6.5 meters? It's really hard to put a 30-meter mirror with the right optical precision in space. And so you can do that on the ground, and if you get your Fraunhofer diffraction formula out and calculate the area disk for a 30-meter mirror, this is a considerably sharper image that you can do with a 30-meter mirror. The only problem that you have with a 30-meter mirror on a mountain on Earth is you have the Earth's atmosphere above you. And so I said we will use adaptive optics, and I didn't take the time to give you a short course in adaptive optics, but we now know how to look at the way we look at our science target in the sky, which is being blurred by the Earth's atmosphere, but at the same time we look at light from something we know is a sharp star, either a natural star or a star that we create with a laser beam. About 100 kilometers up, there's a layer of sodium ions, and we can make an artificial star. So if we have a sharp standard in the atmosphere, we can use a deformable mirror. We can use a wavefront sensor to sense the distortion of that wavefront as it comes through the Earth's atmosphere. And we can use a deformable mirror to correct out that distortion and apply that deformable mirror correction to the science target we're looking at. And that's what adaptive optics is. And the adaptive optics systems will measure the distortion of the wavefront from a sharp object, a standard, a guide star, 800 to 1,000 times a second, and using a deformable mirror, correct the image from the science target and wipe away the disturbances of the Earth's atmosphere. To general audience, as I say, adaptive optics untwinkles the stars. Okay? So we don't need to put TMT in space. We can do it from Earth. We try to pick a good mountain so we have as little of the atmosphere to correct for, but we don't want to make the job hard. But we don't need to put TMT in space.
Professor, I want to know what kind of people are needed in the project like this, except for those who are major in physics, or what kind of knowledge or ability do we have to get to take part in the object like this? Thanks.
Yes, and it's a large number of different kinds of people. I think the diagram that I showed, and I'm trying to flip back to it, that triangle. We need scientists in a project like this. We need engineers. We need business people. This is really the key diagram. For every task in a large science project in TMT, we estimate what kind of work is to be done, what kind of expert to do it, and how much effort there is. And we build up a schedule, and that tells us what kind of people we need. And so in TMT, actually, most of the people are engineers. Mechanical engineers, structural engineers, optical engineers, optomechanical engineers, controls engineers, a very large number of engineers. Some scientists, some astronomers, some physicists, a lot of business people, a lot of experts in quality, in safety, in finance, and management. And so my own office, when the project is at full strength, will have about 110 people in it, and there'll be several hundred people working on the project in all of the countries. It's all those kinds of people. But we build up an estimate of every task and ask ourselves what kind of expert do we need for these tasks, and from that we know what to hire. But they all have to be able to work both as experts in a team and understand the process and decisions and how to make decisions successful. Those are the key skills.
And I want to ask, what are the highest risks in these projects, apart from maybe the malfunction of devices? Mm-hmm. Thank you.
So each project is one of a kind. They're all different. In some projects, the technical problems are really the biggest risk. I think in LIGO, advanced LIGO is measuring at a sensitivity where the mirrors, which weigh 40 kilograms, and when advanced LIGO is at its full sensitivity, it will be measuring the position of those mirrors at the limit of the Heisenberg uncertainty principle. That's pretty demanding. That's I think they'll do it, so I'm not really worried. But I have to tell you, 10 or 15 years ago when advanced LIGO was being designed, and I worked on the design of advanced LIGO, it looked pretty scary. Okay, so I think that is an example of a really severe technical risk. But I think in these projects, if you do the development early enough, thoroughly enough, carefully enough, and I could give a lecture on how you manage the research and development on these projects, you can reduce the technical risks. And so the remaining risks are the organizational, cultural, political, financial, quality, getting every part of the team to produce things exactly with the right quality so that they really work. Those are more serious challenges. So I actually think the organizational and cultural and political challenges are the limits on most projects. And of course, the funding agencies care about cost. We all know of stories of science projects that went over budget and make a bad reputation for all of science. That's why the Super Collider was canceled in the end. The project's cost kept increasing. Not my part of the project, but the accelerator. And ultimately, the political authorities just lost support for the project. So that's always a big challenge. Solve the technical problems first, and then you have the other really hard problems to solve.
I've got two questions. Okay, the first one is that you talked about 3 projects, from SSC to LIGO and then to TMT. So would you talk about actually what happened to SSC in the end, and what made it end up so different from LIGO, which was apparently a great success? And given the current situation of TMT, I mean, no one would question its technical readiness, but given its, the delay in construction and so on, when do you think it's scheduled to be completed, and what do you think is the most likely site for TMT to be built, if not on Mauna Kea? And my second question is, how do you see the role of China in building TMT? Thank you very much.
Okay. The first question had two parts to it, though. I'll answer part of it. The delay on the site is going to cost us 2 years, okay? And so instead of, I believe we will select the site within a year, and I believe that we will restart construction in April of 2018, and that we'll finish the project in 2026. That's about the same schedule as the other large telescope projects in the world. And the other comment I'll make is to get these big projects started and executed almost always takes longer than people think at the beginning, mainly because we are talking about political and organizational decisions. You know, when you have several governments involved in a project, governments don't all make the decisions at the same time. Each government has its own processes, its own fiscal processes, and so on. So that always delays getting the project started and really running. Once it's running, it should be managed with the techniques that I've described. I believe we will finish in 2026. As to which site, I will tell you that Hawaii is a possibility, but we are looking, and you can read this in the newspapers, at sites in Chile, in Spain and the Canary Islands, in Mexico. We have also proposals from India and China. All of these are going to be looked at this year, and I couldn't predict where that's going to go. I'm the person who's supposed to lead the team in the design and the construction, but I think the decision on where to put it belongs to the owners, the scientists and the board of directors that I report to, and I'll let them make the decision. What was your other question? Oh, China's role. China's playing a very significant role in a number of technologies. No one has ever built a 30-meter diameter segmented mirror with aspheric mirrors this large. Clearly, the 36-mirror Keck telescope proves that the process works. But we couldn't afford to build TMT if we made the mirrors the same way as the Keck mirrors. So we have to learn how to make 30-meter, 492 mirrors with 82 spares, almost 600 mirrors with 15, 20 nanometer precision, and they're aspheric, and they all fit the shape of a hyperboloid. Okay, that's very challenging. And Nanjing clearly has the ability to do this. This is cutting-edge technology in mirror fabrication, and I think that's really good example of a high technology thing. The guide star laser effort, there's not many places in the world where you can produce 589 nanometer, 20, 25 watt guide star laser that has the right kind of photon return. I think we have such a capability here in Beijing, okay? So that's very challenging. Boyong is sitting right there, okay? He's leading the team, okay? And I'm going to make the talk short so you can get back to the lab, right? And so I have high hopes that we will produce that laser here in a laboratory in Beijing. The laser guide star facility that will bring the light up the telescope and then create a constellation of 6 to 9 artificial stars around the science target is being designed and will be built by our colleagues in Chengdu, okay? And then this science steering mirror in Changchun, this is a mirror, 3.5 meters by 2.5 meters, and it's flat. And I mean really flat. And if you're an expert in optics, you know that to produce a large flat mirror is really a challenge. Okay? They will do that in Changchun, I'm quite sure. And then it all has to go on to a system that in effect is the same as a 4-meter telescope system, very precise. We're pushing the limits of the ability to move something without jitter. We're finding as we design these things, we're actually designing something that's supposed to work smoother than anything we know that's been built. And we've been doing tests to see whether you can actually do that. We believe it can be done. So these are just four. There's also a cooling process, turbine expander cooling here, TIPC in Beijing, which I think will be a revolution in cooling astronomical instruments and removing vibration from those instruments, which often limits image quality. So I've just given you a few examples, okay?
And more questions?
There's one back there.
One guy there.
Hello, Professor. So you just mentioned the error correction on the ground, right? And we all know that there will also be errors in space, such as errors caused by storm and so on. So my question is, can we say that there will be a day when the disadvantages in the space are greater than the disadvantages on the ground, where all our telescopes will be built on the ground? And I don't know the situation about the error correction in the space. And can you just explain that?
Yeah, so the kind of error correction I'm talking about comes from the Earth's atmosphere. The atmosphere above a telescope is not all of even temperature, which means that the atmosphere has different indexes of refraction, and it's turbulent. And so there are pockets of warm air and cold air with different indexes of refraction, and that causes stars to twinkle. That's the kind of disturbance that we correct out with adaptive optics by measuring the distortion of the wavefront as it comes through this turbulent air, calculating how to curve a mirror to cancel it, and then looking at the science object. That's an atmospheric disturbance. I'm not sure what disturbance you mean in space. There is no atmosphere. And so if you had an optical infrared telescope in space, you wouldn't have this kind of disturbance. But the main part of your question was, will there be a time when the disadvantages of working in space are such that you should build all the telescopes on the Earth? And there won't be such a time, because there are astronomy done at different wavelengths, and not all of those wavelengths get through the Earth's atmosphere. So as you go farther out, you need to get above the Earth's atmosphere. So we wouldn't put Hubble up above the Earth's atmosphere now, but the James Webb Space Telescope makes sense because of the wavelength region that it's going to study. And in fact, it not only has to be above the Earth's atmosphere, but it has to be far enough away from the Earth so it's not disturbed by the thermal influences of the Earth. But there are many kinds of telescopes that have to be above the Earth's atmosphere because the messengers that are being studied don't get through the Earth's atmosphere. So I think astronomy will always be a mix of ground-based and space detectors.
I want to kind of ask a question. About 20 years ago, we both work on the SSC GEM. At that time, we all think this project was very hopeful, but we didn't expect that it's being cut by the Congress. So now, for the other project, can we make this same question? Or we could say the bigger the project, the larger the budget, maybe the higher the risk. Is that right?
I don't know if there's a linear or a relationship like that. And in fact, I remember the other part of your question now, which was what happened, we didn't do the super collider. And I mentioned it very briefly, and I will answer your question. In the team of GEM, when I was the project manager, when the Congress canceled the project, there were a little over 1,000 scientists and engineers in the team. And if you look 2 or 3 years later, more than, I think, 2/3 of them ended up working on the two detectors at the CERN Large Hadron Collider. And if you look at the design of the two detectors at CERN, you'll see the liquid argon calorimeter, you'll see the crystal calorimeter, you'll see many of the technologies that we were developing at the super collider, both in the system I worked on, GEM, and in the other detector, SDC. So the community that was working on the US project largely moved to Europe. So I would say it happened. It didn't get stopped, it just moved somewhere else. And with European commitment and European resources, the system was built, a very good system, and the Higgs particle was seen and the stuff we haven't yet seen will be seen. So I think it was a success. As far as big projects, when I give lectures, longer lectures, on managing big science projects, one of the lectures is called the near-death experience. Okay? Almost all big science projects hit a crisis. Usually it's a funding crisis. In the case of TMT, we've had a political crisis about the site. And many of the projects survive. Not all of them do. And that's why I call it the near-death experience. And I give examples when I give a lecture about that, of what has to be done. But it does depend on the commitment of the sponsors, the funding agencies, and the commitment of the community. And I'll give you an example. On the Super Collider, the Congress did not like the growth in the cost. And the Congress lost support. But also the U.S. high-energy physics community didn't fight hard for the Super Collider because it was broken into groups that fought for SLAC, Fermilab, and Brookhaven. And the Congress saw that the community was divided. That was the end of the project. So a lot of this depends upon the commitment of the community and how much they want to do the science, and the commitment of the owners, the sponsors, to weather a crisis. And I think in TMT we have a very strong commitment, and many of our partners. A lot of money has been invested. I see a level of commitment and consistency that I haven't seen in many other projects. And so I'm very optimistic that TMT will get through the current crisis.
So, Gary, as as eminent project manager, do you actually think about maybe at some stage we will run out of money, for example, to build a 100-meter telescope, or the next stage of a Higgs factory? The funding level will be huge, and the number of people you mentioned, already 4,000, will we run out of physicists?
So that's a great question. And when I look at my own career, which began in the 1960s, and that was a long time ago, when the big projects in the world would fit on this stage. It was already a big project, and now they're many, many kilometers long in some cases. The square kilometer array, the radio array that's being planned for South Africa and Australia, is enormous. A square kilometer of sensitive radio collection is over many, many square kilometers of ground. So having lived through high-energy physics that started with machines that fit on this table, and then to machines as big as this stage, and are now tens of kilometers in size, I am worried. I am worried that we're getting to a scale of machine. The linear collider is an example where we may be testing a size that's just too big, okay? I am worried about it. Now, you can hope for advances in technology. With accelerators, people are working on higher gradient accelerator technologies that may solve that problem. But I do think we are, with ITER, with the linear collider, with the square kilometer array, we're testing what might be a rigorous upper bound on the size of the projects that basic science can get supported. Space projects are more expensive, but they have been supported, I think, because of their relationship to defense-oriented technologies. And so the systems have been willing to bear higher prices, but we may be testing that as well. Yeah.
Does the TMT observation data will open access?
The telescope open access.
Oh, open access. Okay. That's a very good question. The partners, Canada, China, India, Japan, and the two California universities and their supporters will be investing $1.6 billion in the system. And if a partner invests 10% or 20%, they will get 10% or 20% correspondingly of the nights. That's the way the number of nights, 365 nights in the year, are divided up. And so the astronomers from each country will get nights in proportion to their country's investment. Now, the way the system in astronomy has worked at most observatories is when the investigators collect the images or the spectra or the data, they get a period of a year perhaps typically it's a year, in which they have the data and they get the right to publish first. And then after that, the data is released, in some cases, in some observatories, to anyone in the world. In some cases, in the case of TMT, if it's a night that belongs to Canada and they take data, then those astronomers will have that data privately for a year. And then they release it, but to the rest of the TMT community, not to the world. So that's the status for TMT. That may change in the future. There is a push in the world, in most governments, to make all data public, completely public. And the Large Synoptic Telescope, LSST, is a telescope that I think will test that by taking a view of the sky every week or 10 nights completely and then releasing the data. And they're struggling with how to do that in a way that still makes it attractive for countries to invest in the system. I think the progress is towards open data more and more. But the people who invest in these big, expensive projects generally want to have some proprietary interest up front. Radio astronomy is somewhat different. They also tend to open things up more fully after the proprietary period. So we're in a period where the sociology and the culture of data ownership is changing.
Well, Gary, let me take this privilege to ask a question. You do have astonishing and admiring education background and working experience, you know, in those very famous universities and prominent national institutes. So could you tell us some difference among these universities and institutes in terms of their capability or cultural difference in planning or implementing large-scale science project?
I think when you're talking about scientific research, and I'm, of course, an expert in principle in physical sciences, physics, astronomy, and so on, the culture of the university, the culture of the institute, while they may be different, it comes down to picking the best people and then trying to make sure you work with the best people. I think even though I'm talking about groups of thousands of people working together on a given day, it's a team working in one place that's doing most of the work together, and what you want is to have the best people. And so I would say in your own career, try to work with the best people, and the rest will take care of itself. Some institutions, universities, laboratories are very good at supporting people and making sure they get to do what they're good at, and some are less, and that can make a difference between institutions. I've been lucky to work at good ones that did a good job of supporting people. But I really think if I were giving advice to younger people, it's try to work with the best possible people you can.
Go ahead. Hi, Professor Gather. I noticed that many young researchers are attracted to this talk. So I think it's a good chance for you to give some guideline or advice for the young research, whether they become a lone scientist or they are joining a huge cut-edge scientific report, even there's big risk. Thank you.
So I think my best advice is to find yourself, okay? You might be someone who does really good work alone or with a small group. You might be someone who likes working with a large team. You might not know today which one you are. And so my advice is to find yourself. And don't try to go into a model that might not match you. But be aware of it. I tried to show some pictures of different models, achievement, affiliation, power, and so on. Try to make visible to yourself different work styles that work for different people, and try to find what works for you. Okay?
Well, finally, Please join me to thank Gary again for this wonderful talk tonight.
Thank you.